Hello and welcome to the 181 video. This one's on support vector machines, in particular hard margin classifiers. If you remember the binary linear classification video that we did, we talked about if you have a bunch of data points and maybe there's certain people who have gotten a disease and certain people who haven't gotten the disease, and you want to train a model so that given a new person you can predict if they're likely to have the disease or not. And we came with a pretty good model, but one of the issues with the model is that given the data that I've drawn here, it would prefer lines 2 and 1 equally well as decision boundaries. It wouldn't really have a preference between those two. But it seems like line 2 is substantially worse than line 1 here, because if you sort of have this, if you have a bunch of uncertainty in the middle as to where to draw the boundary, you want to split the difference, and because that will allow your model to generalize better. For example, here, let's say that there's another data point right here that's just on the other side of line 2. Well, this person is also probably going to be in the orange category, but since line 2 has such a slim margin on that side, it may misclassify that point. So in particular, we want a model that might be able to draw decision boundaries that are a little bit more fair, that sort of maximize the minimum distance over all the points between that point and the decision boundary. So how are we going to do that? First, an important assumption for today is that the data is linearly separable. When I say that, what I mean is that you can draw a line or a hyperplane, and that will separate the data into two classes. We're only going to be talking about two for today. So what is our model going to be? It's going to be very similar to our previous models. We'll take our data, or here I've written 5x, which is just some sort of basis transformation of x, and we will multiply that by some coefficients and add an intercept. You'll note that today we are actually not using the bias trick as we've done previously, and that's because it's more mathematically convenient to not do that, which you'll see in a little bit why that is. So then if this is greater than 0, we'll predict 1, and if it's less than 0, we'll predict the other class, -1. We'll use 1 and -1 to represent classes today. Great. And for simplicity, throughout the rest of this video, I'm just going to be using x instead of 5x because we can just assume that we're working in the space of the basis transformed inputs. So what are we going to do today? Our strategy is going to be, we want to find the minimum distance over all points between the point and the hyperplane, and then we're going to want to maximize this, right? Because we want to make as large of a margin as possible. And in particular, we're going to do this in 3 steps. First, we're going to say, what does our decision boundary look like? So we can get a better intuitive sense of that. And then we're going to find a mathematical formula for how far each point is from the decision boundary. And then we're going to find and solve for a W and W naught that maximize this quantity, the minimum distance over all points between point and hyperplane. Great. So our model, if WTX plus W naught is greater than 0, we'll predict one class, and if it's less than 0, it'll predict the other class. So that means that WTX plus W naught equals 0. That equation defines the boundary. That's the point where our model goes from predicting one class to predicting the other class. And conveniently, WTX plus W naught equals 0 defines a hyperplane. A hyperplane is like an n-1 dimensional shape. So it's like a line in 2 dimensions, or a plane in 3 dimensions is sort of like the higher dimensional extension of that concept. But just as a quick mathematical refresher, right, to give examples of where this is true, in a line, the equation for that is y equals mx plus b, but we can rewrite that as mx minus y plus b equals 0. It gives us a line, so a 2-dimensional hyperplane, and mx minus y plus b equals 0 is exactly the form of our equation. Or in 3 dimensions, like x plus by plus cc plus d equals 0, that defines a plane. It's just to give a little bit of intuition and connect some of the things you know. Great. So now we figured out what our decision boundary looks like, and now we're going to try and figure out how far each point is from the decision boundary. And in particular, we're going to want the orthogonal distance. If we have a point like this, we don't want this distance from the hyperplane. We want the orthogonal distance from the hyperplane. So I'm going to prove a quick claim, and then I'm going to use that to derive how far each point is from the hyperplane. I claim that our vector w, and this is why we separated out w and w naught, is orthogonal to the hyperplane defined by wtx plus w equals 0. So suppose that x1 and x2 are vectors in the hyperplane. So what it means for a vector to be in a hyperplane is that it satisfies this equation right here. So we have w plus x1 plus w naught equals 0, which implies that w transpose x1 equals negative w naught. And similarly, since x2 is also in the hyperplane, we have w transpose x2 equals negative w naught, which we'll use later. The next thing that we want to observe is that x2 minus x1 is parallel to the hyperplane. And what I mean by that is that since x1 in this diagram down to the left here, we have x1 and x2, and then we have a hyperplane here. And if we take x2 and we subtract x1 in red, then we get a vector in green, right? And that's parallel to the hyperplane. So basically, that's a little illustration in 2 dimensions to help you build intuition for that fact, right? But you're taking 2 points in the hyperplane and you're subtracting them, so this resultant vector will be parallel to the hyperplane. And then if we take w and we dot it with the difference between x2 and x1, then we distribute out, and then using our previous little mathematical fact, we have negative w naught minus negative w naught will get 0. So the dot product between w and the difference between 2 points in the hyperplane is 0. And if the dot product between 2 vectors is 0, that means they're orthogonal. What's important here is that x1 and x2 were just chosen as arbitrary points in the hyperplane. So this means that any 2 points that we pick in the hyperplane, the difference between them is orthogonal to w. That means that any vector in the hyperplane is orthogonal to w, which means that w is orthogonal to the entire hyperplane as a whole. So it's important that this can be any points in the hyperplane, and the proof holds for all of that. Great. So now that we have a vector that's orthogonal to the hyperplane, we can use that to measure orthogonal distance from the hyperplane. So for any data point x, we can split it up into an x projection, which is x projected into the hyperplane, plus a vector that is orthogonal to the hyperplane. So I've drawn that here below. We have this x vector in purple, we have the hyperplane in purple, and then in green we have x projected into the hyperplane, and in red we have a vector that's orthogonal to the hyperplane. So remember our previous claim, w is orthogonal to the hyperplane, and we've just divided by the norm of w, so that w over norm of w is the unit vector. That way we can have a scalar d, and the scalar d gives us the distance between the hyperplane and the vector. So now we want to solve for d, but we don't exactly have a clean equation for x projection, so we're going to pre-multiply by w transpose here, and then w transpose w is just the norm of w squared, and x projection by definition is in the hyperplane, so it means it satisfies the equation, which in other words means w transpose x projection equals negative w naught. So we write that back in here, and then we get that solving for d, w transpose x plus w naught over the norm of w equals d. So that gives us, for any x, the distance between the hyperplane and the data point that we're considering x. Great. And so let's introduce the concept of a margin, which is just the positive distance between the hyperplane and the data point. So this is the thing that we want to measure for each data point. So for some data points, in particular the ones that we classify in the first class, this quantity is going to be positive. So pre-multiplying by yn doesn't do anything, but we don't need it to do anything because we're looking for a positive distance. For some of the other data points on the other side of the hyperplane, this quantity is going to be negative. But luckily, these data points on the other side of the hyperplane are the ones that are classified as in the other class with yn equals -1. So multiplying by yn equals -1 doesn't change the magnitude, but gives it the correct sign. Again, remember, this is for example, an instance of why it was important to say that we're assuming that the data is linearly separable. So there's not some like data point over here on this side of the plane with yn equal to -1. So we can use this as the equation for our margin. So now with the margin of one data point, we want the definition of the margin of the entire data set. And the margin of the entire data set is the smallest margin among all of the data points, right? Because that's the one that we care about. We care about the closest distance between the decision boundary and a data point because we're trying to maximize that. So we can just simply take a minimum over all the data points of the margin of each data point to get that. And overall, we want to maximize this, so we want to choose a W and a W naught that maximize this. So now we've entered sort of step 3 in the 3 steps that I outlined at the beginning of this video. And we're going to try and find W and W naught that that maximize this minimum. And we're going to basically take a couple of steps to move this problem from something that we're not really sure how to solve into something that we have a better idea of solving. Great. So first, I'm just going to prove a fact that will be helpful later. So I claim that scaling W and W naught by beta, which is to say replacing W with beta W and W naught with beta W naught, so just scaling all of that by a certain constant, doesn't change the distances of the data points from the hyperplane. How are we going to do this? Well, we'll take for arbitrary x the function or the formula for the distance between the hyperplane and that point. We'll substitute in beta W and beta W naught. We're going to pull out these betas, and that gives us this beta in front here. The norm of beta W is, I've written it out explicitly here, but the beta will come out of the squared, and then it'll come out of the sum because it's not dependent on I, and then it'll come out of the square root, but we'll just get a normal beta outside, and I've put that here. So we just get normal beta times the norm of W. We'll cancel these out, and we'll see that we get the exact same thing that we started with, which proves our claim mathematically. I think a better way to think about this intuitively, since the math doesn't necessarily give too much intuition, is in 2 dimensions. This line here is my drawing of the hyperplane 2 minus x minus y. Right, so W naught is 2 in this case, and W is -1, -1. And if we scale W naught and W by some constant, for example by 2, to get 4 minus 2x minus 2y equals 0, we'll get the exact same line. We'll get the same hyperplane. So the reason that the distances between the data points in the hyperplane doesn't change is because if you scale both the intercept and the coefficients that define the hyperplane by a constant, it stays as the exact same hyperplane. So this claim gives us the flexibility to exactly scale W such that the below holds, that for the minimum overall data points of yn times W transpose xn plus W naught equals 1. What do exactly I mean by that? Well, as I said before, we're going to try and transform the problem that we're solving into something that is easier to solve. So we have this problem here, right? And that will give us some W and some W naught. And I claim that for that solution, there is an equivalent solution, beta times W naught, such that the value of the objective is the exact same, but also our condition holds. And we know that must be true because of the claim that we just proved. In other words, we can just take the W and W naught that would have maximized this objective and then scale by some beta. We can scale by any beta we want because that'll preserve the objective on the inside, as we just proved in our claim. And we can choose the beta such that the minimum margin is equal to 1. Like, for example, suppose that under this solution, yn times wt xn plus w naught, the minimum of that equals like 1/3. Well, then in this case, we would just make beta equal to 3, and then this the new minimum would be 1. So, and then 3w and 3w naught would also equivalently satisfy the objective function, because our claim says that scaling by some factor beta doesn't change the distances between x and the hyperplane. So in other words, it doesn't change this, so it's not going to change the minimum overall data points of the margin. Great. So what does that mean? That means we can just impose this condition, right? Because for any solution to our initial problem, there's a solution to the initial problem where this condition holds. The thing that you want to be careful of when you're moving from one statement of the problem to the next statement of the problem is, will these give me essentially identical W and W naughts? Or in in our case, it can be identical up to a scalar because, as we said, the scaling W and W naught together doesn't actually change the margin of the data set. So now we're going to go ahead and simplify again. First, I'm going to pull out the 1 over norm of W because it doesn't actually depend on n. And now we just have the minimum margin over the data set. And our condition is that the minimum margin of the data set is equal to 1. So this thing we'll just get rid of because it's just equal to 1. So now we have this. Great. So the next thing that I'm going to do is I'm going to change the constraint a little bit. So I claim that this constraint here, the constraint that we currently have, the minimum margin is equal to 1, is the same thing as the constraint that for any data point, the margin is greater than or equal to 1. And when I say margin here, it's not technically correct, right? That this thing should be divided by the norm of W, but I'm just going to refer to that as the margin because that's the quantity that we're dealing with most of the time. So why are these identical? Well, let's check that under the first condition, the second condition holds, and then under the second condition, the first condition holds. So under the first condition, the minimum of the margin is equal to 1. So that means there can't be any margins that are less than 1, which is exactly what condition 2 says. So it must hold. Now, in condition 2, we see that all the margins must be greater than or equal to 1. But what we want to show is that there is a margin that is equal to 1, right? Because by ensuring that everything's greater than or equal to 1, we know that there's not going to be anything less than 1. So the minimum is not going to be any lower, but the minimum might be higher. We have to show that the minimum of the margins is equal to 1. So let's suppose, towards a contradiction, that the minimum of the margins is greater than 1. Well, in that case, I claim that we can actually reduce W, and so overall, we're not satisfying the constraint that we're at the maximum of 1 over the norm of W. Right? So the fact that we're trying to maximize 1 over the norm of W means that we're trying to reduce W. And let's say that the minimum of the margins under constraint 2 is greater than 1. So then we can just go ahead and decrease W a little bit. All of the margins may fall a little bit, but we have that wiggle room. And so then we can still decrease W, and so thus it must not have been a maximum. So that's a contradiction. So our initial assumption was wrong. So actually these two constraints do the same thing. In other words, 2 implies 1, and we already showed that 1 implies 2. Great, so we're just going to go ahead and substitute the constraint there. Now, we're going to change the thing that we are maximizing, and we're actually going to change it to minimizing. So right now we're maximizing 1 over the norm of W, and I claim that's the same as minimizing 1/2 times the norm of W squared. Well, why is that? So we know that the norm of W is greater than or equal to 0. So the way we maximize 1 over norm of W is by making norm of W as small as possible, which is the same thing that we're trying to do when we minimize 1/2 times norm of W squared. Great. So now we just substitute that in, and we just, right, so now we're taking the arg min over 1/2 times norm of W squared. And now I'm going to rewrite this again. Basically, I'm going to incorporate the constraint so that it's all in one equation. And I'm basically doing a Lagrange multiplier here, but I'll also explain why the new constraint that I've replaced it with is identical to the old one. So you'll see that the first part is pretty much the same, but first we're going to take the maximum over some vector lambda, where lambda is greater than or equal to 0, which is to just say that each of its arguments are greater than or equal to 0 of the initial thing that we're trying to minimize, minus the sum over all data points of lambda n, so the nth element of the lambda vector, times essentially the margin minus 1. So to show that this and this are the same, I'm going to show two main things. First, I'm going to show that, let's call this equation star. So star doesn't violate the constraint, and the constraint is this part of the first equation. And the second thing that I'm going to show is that subject to the constraint, the equation star minimizes the quantity 1/2 of the norm of w squared, because that's what this equation does. It holds the constraint to be true, and given all the w's and w naughts that satisfy the constraint, it returns the w and w naught that minimize this. So first, why is the constraint satisfied? Let's suppose towards a contradiction that the constraint is not satisfied, which in particular means that there exists at least one n such that yn times w transpose xn plus w naught is less than 1, which is to say that this part in here is less than 0. So then we just choose a lambda n, because remember that we're maximizing this internal expression over lambda. So we choose a lambda n that is really very high, and then that means that this sum quantity will move towards negative infinity, right? We can choose the lambda n to be arbitrarily large, so we can make the quantity arbitrarily largely negative, and then the leading negative makes that positive. So overall, that w and w naught, the maximum subject to lambda of this entire thing is just going to be humongous. So it will never pick that w and w naught. Now, to prove the second fact, so subject to the constraint, because it's not going to pick something that's not subject to the constraint, then what will the maximum subject to these lambdas be? Well, if yn times w transpose xn plus w naught is greater than or equal to 1, that implies that yn times w transpose xn plus w naught minus 1 is greater than or equal to 0. And so in order to maximize this, since those positive quantities would contribute to a sum, and then that sum would be subtracted, then lambda n will be 0, or in some cases lambda n can be non-zero if this is an equality, but in that case this term right here will be 0. So all of the terms of this sum will be 0. So we'll just only have 1/2 times the norm of w squared, which is to say that for all the possibilities that satisfy the constraint, the maximized value over lambda will be 1/2 times norm of w squared, and so this will return the minimum w and w naught that minimized 1/2 times norm of w squared. So star and this are do the same thing, which is exactly what we want to show. Great. So now we're just going to use something called duality, which is when you have a maximization problem and a minimization problem, and they give you the same solution. So if you took 124, stuff like linear programming has dualities in it, or if you took 1011, stuff like cost minimization is the same thing as profit maximization. So it's a little bit beyond the scope of the course to go into exactly why we can switch these two things, but we can switch the argmin and the argmax here, and then we keep the same objective function, and I'm just going to refer to this as equation 1. So now this is really convenient, and the reason we want to switch these around is because we know how to minimize this thing on the inside over w and w naught. That's really nice. So we're going to go ahead and solve this first. So first we're going to solve for w, so we're going to take the gradient with respect to w. This first term just gives us w, and then the second term, this minus 1, this w naught, these terms aren't going to have any w dependence, so we can just ignore them because they won't contribute to the gradient. And then here we have lambda n, yn, those are just coefficients we can pull out, and then the gradient of w transpose xn with respect to w just gives us xn. So we can go ahead and solve that. Remember that this is equal to 0 because we are minimizing here, and then this will give us an equation for w. Now we're also going to do a similar thing. We're going to take the derivative with respect to w naught. This first term is not going to matter since it has no dependence on w naught, and neither are these two terms. So we're just going to be left with some negative sum of lambda n yn w naught, and then the derivative of that is just sum from n equals 1 to n of lambda n yn. And you can add this negative if you want, but it's just equal to 0. So we're going to rewrite this as multiplying both sides by -1, sum from over all the data points of lambda n yn just gives us 0. And I'm going to refer to this as equation 2 because we'll need it in a little bit. Now remember, we're not quite done, right? We've minimized this inside part, but we still have to take that function and maximize that function over lambda, where lambda is non-negative. And note, we have not solved for W naught here, but we're going to do that later. But this constraint is still important for the work that we're going to do. So we're going to plug in all of our solutions for W back into equation 1. So there's a norm of W, so we plug in there. And then there's W transpose, so we plug in there. And then that, we're going to go ahead and expand that out. So the first thing that we do, and I'm just going to zoom in a little bit more, is, so the first thing is we take this norm. So this is just the inner product, and by bilinearity, it ends up being the sum over all the possible combinations of data points and of the inner product, or of the inner product between lambda n yn xn for one data point and lambda n ym xm for the other data point. So we have these nested sums, and then we have lambda n yn xn, and then lambda m ym xm transpose. And then the second term here, we can just take the lambda n and yn and move them inside the sum since they're not dependent on m. We can do the same thing with x sub n, and then notice the transpose falls down to the xm. It doesn't, these are just scalars, so the transpose doesn't affect them. So we actually have the same term here, just multiplied by -2. And then we can pull the W naught out of this sum since it doesn't depend on n. And then by equation 2, this is just 0, so this entire term goes away. And then we just rewrite everything together, combining the first two terms. So now we need to maximize this subject to lambda being greater than or equal to 0, and also subject to equation 2. That's our other constraint. So we'll use a technique called sequential minimal optimization. This technique is all sort of summarized at a high level here. Basically what you're going to do is you're going to pick two of the lambdas, and you're going to minimize, you're going to optimize, so maximize with respect to those, and you're going to keep doing this until you converge. We normally just, the more general technique is just to do it one component at a time, but the problem here is that this constraint requires that if one lambda n changes, another lambda n changes, right? Because n minus 1 of the lambdas determine the last lambda according to this constraint. So we have to change two of them at a time. So let's assume that now we've optimized for W and we've optimized for lambda. So now we have W and lambda, but we still need to find W naught. So recall that the original goal was to have the largest margin. So again, as a quick reminder, margin is the minimum over all points of the distance. This equation is the distance from that point to the decision boundary. But we can't actually change the norm of W by changing W by choice of W naught. So we're really just trying to maximize this, which I'll just call this sort of our objective function, because that's what we're trying to maximize. So how should we think about this? There's a couple of ways of going about it, but I think the easiest way to think about this is that there's going to be a closest point on either side of the decision boundary, of either side of the hyperplane. There's going to be a closest point on the side yn equals 1 and a closest point on the side yn equals -1. And so we can write those points out mathematically. So for yn equals -1, we're going to take the minimum over all n such that yn equals -1 of the, here I just replaced yn with -1 because we know it to be -1. And I'm going to use m to indicate the index of the point that is closest on that side. And then for yn equals 1, we can just drop the leading yn because we know it's equal to 1. And so we take the minimum over all n such that yn is equal to 1 of the objective function, and I'll use L there to indicate the point that's closest on that side. So now let's think about intuitively sort of what we want to be doing. So 2 dimensions is great for intuition. Let's say we're trying to set the W naught here, and what W naught does in 2 dimensions is it just moves the hyperplane around. And so there's going to be some point that's closest on either side, and intuitively, probably what we want to do is split the difference. We want to equalize the difference, the distance to each of the points, the closest point on either side. And so the closest, we can do that by just setting these two equal, and then we'll solve for W naught. So we'll add W naught to both sides. We'll subtract WT W transpose XL from both sides, and then we'll end up dividing everything by 2, and that gives us a clean solution for W naught. So I claim that this is the W naught that we should pick. But you might not necessarily be convinced of that, and we're going to go ahead and actually prove it. So if we choose that to be our W naught, then the distance to either of the points is the same, and just plugging in for W naught, we get W transpose times difference between XL and XM divided by 2. Now, what if we choose a W naught that is greater than this? Well, in that case, I claim that we are closer to the point M. So just distributing the negatives out, and then this implies that negative W naught is less than W transpose times XM plus XL over 2. And so we can just, so that implies, right, that negative W transpose XM minus W naught is less than negative W transpose XM plus W transpose XM plus XL. So I just substituted, and then for negative W naught, and since there's this inequality, then the inequality holds between the substitution. And this thing on the right here just simplifies down to that. And so we see that actually that's the distance that we get when we equalize when we pick the midpoint. And so the point M is actually closer. It has a smaller margin. So that's less preferable. And let's say that we pick a W naught that's greater than, that's less than that. Then in that case, I claim that point L is closer. And point L, we can just, again, using the inequality and substituting, we get that the distance to point L is less than the distance if we were to just pick the midpoint. So we see that this is the optimal W naught. So let's sort of put all this together by talking about how our model will work. So once we've solved for W naught, and the lambdas, what will our model actually be doing? We're calling our prediction function again. Remember that we take W transpose, we multiply by X, and then we add W naught. And then depending on the sign of that, we predict either the first class or the second class. And also remember from our gradient that we solve for W in terms of lambda. So plugging our equation for W into our prediction function, we get that predicting on some data point xi, some new data point, we have the sum over all the data points of lambda n yn times, and we're going to put phi back in here. It'll become clear in a second, y, phi of xn transpose times phi of xi plus W naught. So the first thing that I want to observe here is that lambda n, we actually know sort of what values this is going to take. And I've drawn a little diagram below to give you a better picture of overall what a support vector machine, in particular hard margin classifier, is going to look like. So we have some group of points in red, some group of points in blue. We have our decision boundary in purple. And we have, remember that in our choice of W naught, we split the difference between the two closest points. So there's 2 points that are in particular, remember we chose to multiply beta times W in order to make these distances both equal to 1. So the closest vectors are unnormalized distance to the decision boundary is 1. And that connects with something that we were talking about earlier. Remember that when we talked about why this constraint is valid, we said that if the constraint holds, then we know that yn W transpose xm plus W naught minus 1 will be greater than or equal to 0. And in fact, we know that for most of the point, for any point where it's greater than 0, and that's a strict inequality, then lambda n has to be equal to 0 because we're maximizing over lambda this internal objective function. And if it's strictly greater than 0, then this is strictly positive. So then, since we're maximizing over lambda, we have to make lambda 0 so that we don't subtract from our objective function. So the only time lambda is not equal to 0 is if yn times w transpose xn plus w naught equals 1. And that's only true for for the points that are closest to the actual decision boundary. Note that it's possible that there might be a couple of points that are all tied for being closest to the decision boundary, but the important takeaway here is that this lambda n is 0 for all other data points. So even though we have a lot of data points, the only thing that we really need to predict for new xi's is the data points that are closest to the margin, the one that essentially define exactly where the margin is placed. We call these the support vectors, and that's why overall this technique is called support vector machine. So that's one thing that makes our calculations really convenient. But the other thing is that this is an inner product here. And sometimes our basis functions might be kind of complex. Maybe we're going from R5 or something to R25, and we're drastically increasing the dimensionality. Well, that will also drastically decrease the speed of the algorithm, but if we're careful with what sorts of transformations we use, we actually don't need to go through the process of transforming the input vectors. We can just have a kernel function which directly calculates this and is much, much more efficient. So that's an advantage of having these lined up as an inner product. So the last thing that I wanted to talk about is that this advantage of kernelized functions actually comes from the fact that we use the dual problem. So remember up here, we originally had argmin of a max over lambda, and we turned this into max of an argmin by using the dual problem. So this initial problem is actually just a quadratic programming problem, so it is solvable, and it's relatively comparable to how we would solve our dual problem naively, but the fact that we use this dual problem allows us to get values for our lambdas, and most of these lambdas are 0. So that's convenient because it means that we don't have to calculate this for a lot of data points. And the second thing that it does is it gives us a solution for W in terms of a weighted average of the data points. And that means that conveniently, our prediction function will basically, most of the calculation will need to be done as the inner product of x vectors, and that can be done by the kernel function. So note that intentionally our choice to use the dual here allows us to have a more efficient prediction function.